My name is David Robbins. I'm an engineer in the inertial team here at Parker.
My name is Nathan Miller. I'm a software engineer here at Parker working on the MicroStrain product line. So the background of the project is we recently released the GQ7, which is a GNSS INS with RTK capability. And that RTK part of it really gives you high accuracy positioning. And so we wanted to kind of convey that in a compelling and fun and interesting way. So the original idea for the project was to use our drone and to spray an ecologically safe spray paint over a surface and do a line drawing. But very quickly, Dave pointed out all the reasons why that was a bad idea. And so we kind of got together and thought about how to tell the story of precise positioning in a really interesting way. And over kind of a long discussion, we came up with the light painting project.
We'd seen some examples before of long exposure photography, and we wanted to try and bring the precision of our inertial system to that sort of art and see what sort of pictures we could create combining those two technologies together.
If you're trying to decipher what we're actually doing here, we're taking an image that you normally view on your screen. It's a collection of pixels that has a certain width, a certain height. You can kind of imagine that as being a grid of color, right? And what we've done is we've taken that grid and we've mapped it to the ground. In this instance, we're a parking lot. So it's a physical space that we've mapped this grid to. And each of the grid squares is only 1 centimeter in size. So every pixel of that image maps to a physical location that's 1 centimeter in width and 1 centimeter in height on the ground. What happens with the system is as you traverse this LED strip through this grid, it will turn on each LED to the correct color at the correct location and turn off the LEDs if they're not showing one of the image pixels.
So the main challenge for a project like this is being able to meet the accuracy requirements to be able to light up an LED in such a small area so precisely. And on top of the positional accuracy requirements, you also have this attitude heading requirement that's put on it as well. It's not a single pixel, it's a whole strip of them. So as you rotate in space, you need to not just be mapping the center pixel, but the ones at the very end of the LED strip as well. So your attitude becomes just as important as your position. There aren't a whole lot of systems out there that can provide that sort of performance. You need to have things like RTK GPS, dual antenna heading to be able to meet these requirements. So this sort of project mapped perfectly with the new performance that we were able to achieve with the GQ7 on release.
Yeah, and I think it's important, like we're not using anything other than the information coming out of the GNSS INS system. So we're getting that good RTK positioning. We're not using odometry. We're not using external camera reference. We're not using LiDAR or radar or anything on the robot. The only thing the robot knows is the information that it's getting from the GQ7.
When we first started this project, we weren't planning on using a robotic platform. We were actually just having a person carry around the light strip and do the same thing where they were traversing the image area. It became very quickly apparent that having a person operating that just didn't get the repeatability and trajectory accuracy required to be able to make these images come out well. From there, it was clear to us that we had to turn to an autonomous system, one that was much more repeatable, and that's when we started bringing in our Jackal robot to really be that platform that could give us this trajectory accuracy, that could give us this performance. And the great benefit this brought was us getting experience integrating our products into the ROS ecosystem. ROS is important to us as well as being important to a lot of customers. And having experience on our side of really putting together an application project like this really helps improve our ROS driver, the customer experience, and our products as a whole.
Another challenge that we came across was the camera work. We actually didn't think too much about it originally, but we need really good images to portray the accuracy of the system. Otherwise, it won't really tell the story. So we had originally put a camera up on the roof of our building, pointed down at a parking lot, and I had to find the right f-stop value and work through several different runs to try to determine the best camera settings for the job. And then we decided, let's put the camera on a giant boom. So we rented a boom, we put it out there, and we wanted to get rid of the perspective that the camera off of the building had, which is about 45 degrees down. We wanted to point straight down. And one of the things we discovered when we did that was that it made the image slightly worse. And this was because there's a little bit of distance between each of the pixels that we're lighting up. And so if you have color, no color, color, no color, and you repeat that over the entire image, you end up graying up the image. And it just didn't turn out that well. So what we ended up doing in the end is we backed the boom up from the area that we were operating in, pointed the camera at an angle just like we did when we were on the roof, and then got the image that way. And it ended up being a much crisper and clearer image, because instead of getting that, let's say, from your perspective, color, no color, color, basically it moves like this in the camera view, so you get kind of a continuous color as you go back.
Another main challenge that we had to deal with here was really getting the most out of the RTK system. RTK, really, the best accuracy requires a clear view of the sky. When you're operating in a parking lot around buildings and trees, finding a trajectory that really allows you to get a good RTK fix throughout the entire trajectory was very challenging. So finding the exact location to set this up and run it to get the most accuracy for the entire length of trajectory was really challenging.
One of the really interesting things you can see in the images we produced is the effects of multipath. And multipath is the primary error source when you're dealing with an RTK system. And if you want to know what multipath is, basically, if there's a satellite here and you're down here, the primary signal goes straight down to you. And if you receive that, that's great. But if you have a building or something else that's reflective to RF energy, it will come down, hit the building, bounce off, and then go into your antenna. And the reason why that's a problem is you need to know that straight line distance between you and the satellite. And if you don't receive that, what you're getting is something that's a little bit longer than that distance, and it will cause an error. And you can see that in the images we produce, because we have a building that we're operating next to in this parking lot. And if we set the image further away from the building, you can actually see that it paints it with really high accuracies. And as you move that image closer to the building, you'll see some tearing in that image. And what that tearing is it's a reduction in accuracy due to the multipath effect.
So that's something that's cool about these pictures, is they both show the upper limit on your performance you're going to see, and they also can show a visual representation of some of these errors that might creep into these sort of GPS-based systems. And one of the hard parts about moving to that robotic platform was trying to find a position controller that would work well and allow us to get the accuracy we needed for these trajectories. When we started off, we just used the traditional ROS move base package, which is really the first place to go for a lot of navigation type applications. Unfortunately, we weren't getting the accuracy we needed with that. So we actually had to write our own controller, one that was able to much more precisely hold these patterns that we were trying to draw. And you can see the progression as we go through our images, how it gets better over time, and also just even smaller things like how much faster we're able to iterate over pictures with our new controller, those sort of things. Something else we explored with these images was also looking at what happens when you turn off RTK and seeing a visual representation between an image created with RTK and without. And you can really see when you go from centimeter level error to meter level error, visually what that looks like and how that could affect in a lot of customer applications. A meter still seems pretty accurate, but when you're aiming for things like doorways or avoiding obstacles, a meter just isn't good enough. And I think a great benefit of this process of working through the ROS ecosystem is just learning more about robotic navigation, learning more about the ROS environment, and really how to improve our ROS driver, the ROS experience for our customers. And this was really invaluable in figuring out how to really improve our products and how they're used in robotic systems. So obviously, the simplest application of this project is doing something in 2D, but something that's great about an INS system is it allows for 3D navigation. So an idea for the continuation of this project is how do we scale up this sort of long exposure photography, this sort of light painting activity to 3D? Rather than using a ground robot, using an aerial vehicle and painting 3D volumes and structures and landscapes. And I think there's some really cool stuff that we could do continuing this project into a higher dimension.